Good afternoon and welcome to our webinar this afternoon focusing on the thermal management of electronic and electromechanical products with ANSYS. I'm Brian Miller and I'm pleased to be joined this afternoon by my colleague Joel Thacker. For any of you who are not already familiar with wired analysis, very briefly, we've been involved in engineering simulation for now 35 years. We focus on three technologies: simulation, safety and reliability analysis, and also how that can be extended to design and the optimization as well. Over this period of time, we've worked with around 1,500 clients, providing a combination of software, training, and consulting services. Within our team of around 55 staff and associates, we support 7 main software solutions: ANSYS, which were a general purpose FEA and CFD package, which obviously we're talking about this afternoon, together with FlowNex, which again we're mentioning this afternoon as a 1D fluid flow systems tool. We also have other solutions for manufacturing simulation, deform and mold flow, Optimus for optimization, Plaxis for soil structure interaction analysis, and finally Reliasoft, which is a very popular tool for all aspects of reliability engineering. I will now hand you over to Joel.
All right. Good afternoon, folks. Thanks, Brian. Right, so today we're going to be talking about simulation in the electronics industry, mainly thermal analysis, with the focus on electronics cooling. The reason for simulation in the first place, well, why do we care about it? The reason really stems from the fact that what we find is that our electronics designers and our clients are no longer sitting in an office completely isolated from other departments. Very often we find that the product, whether it's a PCB, whether it's a data center, or whether it's an inductor, the product is driven by various departments in parallel. What that means is that you need accurate data to go back and forth between these different departments. It could be a structural department that needs to know what the structural response is. It could be the electronics department that needs to make compromises on currents and volts going in. Or it could be the fluids department that have to worry about what size fan needs to be put into, let's say, a hard drive, or again, a data center, just to keep things cool. So you need to have this conversation in parallel happening between various departments. That in itself leads to a very multi-physics type approach to simulation, and that's where simulation comes into its own, because you can have a single analysis being used by various departments quite easily. If you're going to use simulation, if you're going to use software, obviously you want something that's easy to learn and easy to drive. It also should be parameterized by non-experts. What we're finding increasingly is that within our clients, within, let's say, the electronics department, you have one person who really knows how to drive simulation, whereas there are other 5 or 6 people within the department who don't really want to play with the software, but occasionally want to play around just enough to see what happens if they change the current, what happens if they change a geometric dimension or a boundary condition. So the software needs to be set up in such a way that once the model is set up, someone else can easily come in, change geometric parameters, change boundary conditions, and the software will simply go ahead with the analysis, a multi-physics analysis even, that couples structures to fluids to electronics if required. The software also needs to be customizable. Very often we find clients who are limited to one type of product, or who are working on one within one industry only. It would be handy if they can generate their own GUI, so that someone else who comes new to the business knows exactly how to drive the software also. Last of all, the software needs to be accurate and fast, and the key word over here is fast. Getting a solution is all well and good. Getting an accurate solution is all well and good, but you need that in a timely fashion. So that's where ANSYS's HPC capabilities come into play also. Within ANSYS, regardless of whether you're working on the structural side, on the CFD side, or on the electronic side, we can model items and products that are on the nanoscale level all the way up to, meters long of data centers. So we cover the entire length scale, if you will. Okay, typical electronics cooling applications using the ANSYS software suite. We have trace layers within PCBs. You can model fan units within CPUs, within hard drives. Where do I put my heat sinks? How many heat sinks do I need? How big the heat sink needs to be? What kind of fans do I need? Is the fan delivering enough flow rate? What happens when an avionics box is taken to altitude? How does the fan cope with that? Also with motors, we get power losses coming off motors. That needs to be translated into some sort of temperature and thermal analysis. And then again, inverters also. Do things come into contact with each other when things are heated up? Does that cause some sort of short circuiting? Does that cause excessive deformation? We need to know that. And again, across the ANSYS software suite, you can combine electronics with FEA, with CFD to get a complete idea and a complete understanding of what's going on. Okay, so let's talk specifically about thermal analyses. You've got 3 or 4 different routes really to a thermal analysis on an electronics component. The first being CFD. CFD really matters when you've got convection, conduction, and radiation in play. Convection being the main driving focus over here. Within the ANSYS suite, you can model these 3 phenomena using Fluent, CFX, and IcePack. And we'll talk a little bit more about IcePack as the webinar goes on. On the FEA side of things, you've got mechanical. Again, ANSYS has a wide array of capabilities on the FEA tool set. So, depending on whether you're in the linear or the nonlinear range, you have a license available. You can couple CFD to FEA quite easily, and that's a two-way coupling. Or you can drive the entire system using electromagnetics. So within the electromagnetics package, you can send in your input volts, your input currents, and then that can drive your CFD and that can drive your FEA analyses. Alternatively, you've got a systems level approach. In ANSYS, we have Simplora, which is our electronics systems package. Again, if you're not interested in the details of the components, or if this is a very top level design, that's where systems analysis comes into play. So Simplora works in the electronics industry with circuits, with PCB board layouts, for example. And Flownex is the equivalent, but on the fluid side of things. I want to mention over here that Flownex is not an ANSYS product. However, Flownex can link directly into ANSYS Fluent and into ANSYS Mechanical. So you can drive the entire system, the entire process from Flownex itself. There is also a new system, a new link being built as we speak between Flownex and IcePack, and that should be out pretty soon. In all the cases above, so regardless whether you're using CFD, FEA, EM, or systems, or some sort of coupled approach, ANSYS and Flownex allows you to work in a steady state or a transient fashion. So you can analyze what happens with heat up and cool down, or you can see what happens to a component when it reaches an equilibrium temperature or an equilibrium current state. Okay, just a reminder about today's webinar. I've talked a lot about different packages. I'm not actually going to go into the details of every software tool that we've got over here. I'm just going to highlight those capabilities that are relevant to the electronics thermal industry. If you are interested in more information, feel free to visit our website, our YouTube website, and there are some webinars already on there which you can look at. Okay, so starting at the top then with CFD. I mentioned we're going to talk about IcePack, and the reason for IcePack is because it's really built for the electronics industry. It is the quickest available route to generating a mesh to getting a result. IcePack, I want to mention, is based on the Fluent engine. So it is a robust, well-known CFD solver that's running the program. Like I said before, it can model radiation, convection, and conduction. In terms of what you can do within IcePack, you can build your own model, a CAD model within IcePack from scratch, or you can pull in CAD, external CAD packages, external CAD assemblies from Creo, SolidWorks, Autodesk, or any of the other major vendors. Talking a little bit more about CAD, the reason why IcePack lends itself so well to the electronics industry is because you've got templates already built into the software. So as you can see in the image over there, we've got a template for fans, a template for blowers, for heat sinks, for packages, for openings, for grills. So you don't have to build the geometry all the way from scratch. You can set, how big your heat sink is, how many fins you need in there, or in terms of fans even. We have a vast library, that covers Panasonic fans, Nidec fans, Sanyo fans, and the same goes for blowers, same goes for heat sinks. Anything that you don't find within the IcePack library, you can create one time and then save it to the library and to pull it up again in different analyses, at later stages. We can model IC packages coming in from external parties, so VGAs, FPVGAs, and TBVGAs. It also supports board formats, and we have the ability to import ECAD drawings for any trace analysis that you want to do, and I'll talk more about that in a second. So let's start at the small scale level. Let's start, at the chip level, basically, where you're interested in, for example, PCBs, which is a fairly common occurrence in the industry. We find a lot of our clients are interested in keeping PCBs cool. Basically, what is the junction temperatures, for example, what's the trace temperatures? And these are usually multi-layered board made of dielectric material with several layers of copper. Now, you can model a PCB one of two ways. The first way is you say, right, this is my trace distribution on the board, and you make an approximation that says it's homogeneous material, and I'm not really going to take into account the spatial distribution of the trace. I'm just going to say there is trace material on here, and I'm just going to assume that it covers the entire board or part of the board, and the thermal conductivities are pretty much equivalent in all directions. The better way to do it is where you take the trace distribution, the spatial distribution, and you actually account for that. The minute you start accounting for spatial distribution of trace material, you're essentially locally varying the thermal conductivity. And within IcePack then, you have two subroutes, if you will. One is you can use the conductivity map and do a thermal analysis on that using that conductivity map. Or a more accurate way of doing it is route 2, which is where you explicitly model the traces. So that's where you're doing joule heating or trace heating. Okay, so if we're going to analyze a PCB, I'm going to show you how we can import a board model and traces into IcePack, and what information is coming into IcePack from an external package. So the trace layers can be added on later. When you're bringing in a package into IcePack, you can filter by size, type of power. So for an example, you can say I only want the resistors, I only want the inductors, I only want the capacitors, or you can say nothing below 5 millimeters comes into this model. And that's really handy because depending on where you are in your design analysis, you might find that some things matter, some things don't matter to the overall thermal performance of the component or the system. So omit those since they're not important. They'll save you time on the simulation run. Alternatively, you can bring in custom components. So you might only want one or two of the entire range of capacitors that you've got on the board. You can bring that in. Obviously, with anything that you bring in, it's automatically picking up library information from the board. So in terms of powers, junction resistances, etc., even materials. But if you wanted to change some of the powers or the junction modeling, if you will, during the import, you can do that also. Once you've imported, it gives you an import summary, which is quite handy. It's almost like a checking mechanism to make sure that you've brought in the right number of geometries into IcePack. Okay, so this is our board that we've imported into IcePack. And one of the things you see is that everything is listed in groups and individually also. So if I click on any one of these individual components over here, you'll see that the data is coming from there. Let's look at groups first. So it's combined all the capacitors, for example, all the inductors together. IcePack is pretty smart. It can do that automatically. If I click on any one of the individual components within a group, you'll see that it's already got values, and it's picked that up from the library, from the external package. Again, this is just another component in another group. Again, the data is already there. Okay, so if I go down to individual components again in some other group, I can actually change the total power, for example, because that information was not available to me during the data import into IcePack. So I can do that on the fly within IcePack itself. Okay, let's interrogate the trace layers. You can either bring in the trace layers with the board, or you can bring it in after the event. So that's our trace layers. That's what it looks like. Pretty complicated, pretty intense looking traces. Oh, there's several layers of traces, in fact, has come in on that board. Once we've got the trace, we can interrogate the trace for metal fraction, for example, which is what you're seeing over here. And again, before we even run the analyses, this is again a good way of just saying, where are my metallic objects? Where do I need to place heat sinks, for example? Where am I going to expect most amount of heat to be generated on this board? Okay, so let's compare two cases. So the first one is where we run a thermal analysis. We've input some current and some voltage, and this is the case where the traces themselves have not been explicitly modeled. So what we've done over here within IcePack is accounted for the spatial variation and spatial distribution of the trace material, and then we've lifted off the thermal conductivity from that spatial variation and used that thermal conductivity map in our thermal analysis. And that's what it looks like at a given elevation within the board. If we actually added one of those traces, and that's one of the traces that are highlighted over there, you'll see that the temperature at the same elevation on the board looks quite different. If I put that onto the global schematic, you'll see that the results are quite different. Now, the obvious question over here is, how do I know what to do? And the answer to that is, it depends where you are in the design analysis. If you're just playing around with heat sinks or geometric parameters, just want to get a first look on what's happening, then maybe you don't need to do the trace layers. But on the other hand, if this is if you're further down the line in the design, maybe trace layer modeling, explicit trace layer modeling is something you want to consider. Obviously, trace layers are going to take more time to compute, so that's another issue that you need to think about when you're modeling trace layers. So that's on the small scale. Let's move on to the large scale, which is a data center. Within IcePack, there's a data center module. So you've got ways to model crack units. You've got ways to model tiles, perforated tiles, vents, fans, whatever you want to put into a data center. Like I said again, this is why IcePack is used ahead of Fluid and CFX, because these templates exist already within the software. So what do we have here? We've got 35% open area fraction tiles that are at the bottom. We've got 2 crack units delivering flow rate at a certain temperature. We've got some high density racks spitting out 7 kilowatts. And we've got some other racks at 3 kilowatts, again, delivering a certain amount of flow rate coming in and out. We've got some overhead vents that, air can move on past into the ceiling. And we've got a PDU that's also delivering 3.6 kilowatts. Results, Because IcePack is a full-fledged CFD package, we can monitor things like temperatures, velocities, or humidity, even, for example, at certain locations within the data center on certain surfaces, or you can even generate your own variables that you might want to monitor during the analysis. So if I just show you what's happening over here, you've got cold air coming in from the bottom, going through the tiles, reaching the racks. The racks themselves are black boxes over here, so we're not modeling flow through the racks. We're modeling flow as it enters the racks and leaves the racks and around the racks, basically. So it gets heated up, and you can see warmer air basically moves away from the racks. It moves up to the ceiling, travels along the ceiling, through the vents, up into the upper ceiling, basically, and then comes down into the crack unit, and the process is started all over again. So that is, a large-scale analysis using IcePack. Okay, the other use of simulation is what-if investigation. So once we've built a model, we want to see what happens if we change geometric or operating conditions. So this is a simple example where we've got an electronics box with components on top of it, on top of the board, delivering heat in various ways. And we've got a heat sink on top of it, and another unit also delivering heat. We've got an open grill on one side and a fan. Now the fan is what's being parameterized over here, the location of that fan. So it can be either in this location, in that location, or there. And because this is a fan, we obviously need to give it a fan curve. As I said before, within IcePack, we've got our library of fans, or we can import our own fan and save it to a library for use later. Okay, so the results are right here. You can see, as you change the location of the fans, the temperature at some given elevation within the electronics unit is quite different depending on where the fan sits. Now this is just a geometric parameterization, but we could have easily changed boundary conditions, change the altitude at which this electronics box operates, and that again will change the behavior of the entire unit. Okay, so far we've talked about IcePack on its own, but IcePack can be used with the other ANSYS packages. So we can take IcePack and couple it to static structural to not just get the thermal response, but also the static structural response or a transient response to a component. I just want to talk a little bit about the structural analyses that are available in ANSYS. The reason we go down the structural route is because we're interested in the structural response from a thermal input, basically, that might have come out of IcePack. Within ANSYS, we can model linear, nonlinear deformation stresses, also drop tests on heated components. That's quite important because the way an object behaves when it's cold is quite different to, obviously, when it is heated. So some things that may not be in contact when they're cold could be in contact when they're heated, pre-stressed, and maybe when you drop it then, things fail. As you switch, circuits on and off, you're inducing cyclic loadings on the component. What happens in terms of fatigue to that? Again, contact is a major issue because you could have short circuiting happening within a component. Okay, so let's look at a simple example over here of a graphics card. And what we've got here is the CFD temperature that is taken from IcePack. So IcePack has run. We've got CFD temperature, and that's mapped onto the FEA mesh. One thing I want to point out over here is that the FEA mesh and the CFD mesh in IcePack don't have to be similar. The closer they are, obviously, the better, but they don't have to be similar. Once you've got the input into the FEA package, which is your thermal input, your thermal boundary conditions that have come from IcePack, you basically go about doing a regular FEA analysis, and you get the stress shown in the third plot down there. I just want to point out that the stress contour plot has been magnified by 250 times, so which is why you're seeing gross deformation over there. Yeah, it's not really that bad. Okay, so that's an example of where IcePack is coupled to the FEA package within ANSYS. Obviously, you can have a complete multi-physics model where Maxwell, which is an electromagnetics package, a low-frequency electromagnetics package, drives IcePack, which then, the results from which are taken on to a structural analysis. And this can be, steady state, or this can be full transient dynamic. It doesn't matter. A little info about the electromagnetic packages within ANSYS. We've got a wide array of tools. So we can cater to gigabit communication. We can cater to, again, links to third-party EDA, high-frequency, low-frequency electromagnetics, parasitic analyses, systems-level approach, and I'll talk about SimFlora in a second. But then also, power and signal integrity, system on chips, RF microwaves, or ANSYS PE Expert, which is basically dedicated to the analysis of transformers or inductors. So again, like I said, a wide array of capabilities, and all of these can work in a multi-physics environment, and all of these can talk to the other ANSYS packages. Okay, what I've got over here is an example where we've coupled FEA to electromagnetics. So it's an example of an IGBT. There are 6 legs. We're just going to look at one leg. Typically, these IGBTs are carrying high current for fast switching applications. And the issue is, because you've got high current and quick switching, it leads to thermal stresses in the bond wires, which then are the first things to usually break. In the electromagnetics package, which is ANSYS Maxwell, the conductivity of the bond wire material is temperature dependent. That's important because as the temperature changes, the electrical and magnetic properties will also change. So that has been taken into account within Maxwell. Okay, so we've got our terminals on one of the IGBT legs. We've got diode components, and then we've got our actual bond wires that we're interested in. So what's actually happening over here? First off, the electromagnetics package, Maxwell in this case, is solving the EM field. And not surprisingly, if we zoom into the bond wires, the current density is highest over there for some given boundary condition and operating condition. Those losses are then exported to ANSYS Mechanical. ANSYS Mechanical goes ahead and does a thermal analysis. That thermal analysis result is then taken back to ANSYS Maxwell. And what's happening over here, this is the key part, because these updated temperatures now are used to update the conductivity of the entire system within the electromagnetics package. Maxwell updates losses based on the new temperature data, and then it sends it back again to Mechanical with a new loss, and Mechanical will continue to perform the thermal analysis. So this keeps on going basically until you reach some sort of steady state or quasi-steady state temperature on the bond wires or the chipboard or any other or any other component that you're interested in. Once we've got a steady thermal analysis, the thermal analysis itself, the results of that can be taken to a structural analysis where we can monitor and evaluate the stresses within the system and see if the bond wires indeed are going to fail or not. Okay, so far we've talked about 3D modeling, but in some instances there is a need for a systems level model, a top level model, and on the electronic side we've got ANSYS SimFlora. So what do we have over here? We've got 3 voltage sources, 6 diodes, a capacitor that's going to ground, current meters and voltmeters just to measure what's happening within the circuit, a motor that is driving the entire circuit basically, and we've got some control logic within ANSYS SimFlora that controls which IGBT comes on and when it goes off basically. So again, this is not 3D modeling, this is systems level modeling. Could be used earlier on the design or later on in the design, and can be again coupled to the other 3D solvers. Okay, and those are my 6 IGBTs over there. Okay, now with my systems model, if I just go back over there, I can model this circuit, this entire circuit over here, using some IGBT characteristics. But what would be nice is if I'm working with a certain type of IGBT, for me to be able to characterize and save that to a library such that I can work with that, on this project or any other project, basically. So that's what I've done over here. I've taken an Infineon IGBT. I've given it, the characteristics of the IGBT, the impedance, the transfer impedance, the freewheeling diode characteristics. And once I've done that, it saved it in the library. You can see the highlighted IKW class IGBT that I've created. And it's got its own symbol too of how it's connected and how it interacts with the rest of the world, basically. Once I've got this system level component, I want to just test it out and make sure, whether this thing is actually working the way I think it is going to work. So I can model it in a dynamic behavior, which is a transient analysis where I take into account, the pulsating of the IGBT basically coming on and off, on and off. And you can see that in the junction power, graph, things are coming on and off. Or I can do a steady state type analysis. If I give it a sampling rate of, in this case, 1 millisecond, you'll notice that the junction temperature pretty much stays, there's no difference really between a transient and a steady state type analysis on the junction temperature. So maybe I should have gone with a steady state analysis. At the same time, because this is a steady state analysis, I'm not capturing the pulsing on the junction power, the switching on and off. Again, this might be an issue that I'm not worried about, so I can use a steady state analysis. Again, in Simplora, you have the option to go both ways, dynamic or steady state. You can obviously, once you've got your IGBTs characterized, you can run a systems only model, or you can couple that to IcePack. So in this case over here, I've got an IcePack model built somewhere else, and I want to use this circuit to drive the temperature that's coming into one of the IGBT pins. So this over here is my graph monitoring one of the pin connections, basically the temperature on the pins, and the temperature, and this data is going to be taken to IcePack, and then I run the IcePack model. So that's the IcePack model built offline. That's my temperature graph. I want to talk a little bit about the IGBTs. I mentioned before that there was a control logic on this, on the Simplora model. What's actually happening is that no two IGBTs can stay on at the same time. So we've got one IGBT that comes on, there's a delay. Number 4 comes on, there's a delay, and then number 1 comes back on. And just to make sure there's no short circuiting. If you run the analysis, you'll see at the bottom that no two IGBTs stay on at the same time on the diagonals, basically. None of them stay on at the same time. Obviously, I can monitor my temperatures, my junction powers as a transient phenomena. If I zoom into the pin temperature on the IGBTs, there you go. I can add in my own markers just to see what the actual values are on the graph itself. And each time I interrogate the graph and get a value, it posts it at the top left-hand corner, basically, which can be exported to Excel. Okay. Another systems model is FlowNex. I mentioned earlier, Simplora works in the electronics world. FlowNex works in the fluids world. It's not an ANSYS product, but it does have links to Fluent, Mechanical, and there's a link built into IcePack. So this is a systems model of a data center, upstream, I guess, of a data center. What's happening here is hot fluid is coming into the chiller system, and we need 18 degrees to be sent back. It's a water chiller, basically. 18 degrees needs to be sent back to the data center. There's a sensor upstream of the pump that delivers to the data center, and it basically monitors the temperature that's going back to the data center. If it's not 18 degrees, one of two things can happen. Either we change the flow rate on the chiller, the refrigerant flow rate on the chiller, using a PID controller, or we start opening two other paths, which is the chiller return path or the balance line, basically. There is a valve. You'll see a blend port percentage opening icon, and this valve basically controls how much fluid is coming in, how much fluid is coming in from the chiller return, and how much is actually going off from the balance line, from the bleed line. So it's a transient model. We've got custom pump curves that we've imported into Fluent. We've got PID controllers. It's an interactive GUI. One thing that we haven't done, but we could have done, is optimization and sensitivity analysis to see, do we need to change the refrigerant type, or do we need to change some other geometric parameter? So if I just go through this very quickly, this is our initial state where we're at 24 degrees, and you'll see the blend port opening and closing. Ideally, we need to hit 18 degrees on the left chart, and you'll see that's happening by opening and closing the blend port. And also we need 20 degrees, which is the right-hand chart, to be entering the chiller unit, because the manufacturer has guaranteed if 20 degrees comes into the chiller, 18 degrees will go out. So those are our two things that we're interested in. If we change the temperature to 20 degrees, as I did with the knob over there, again, the system is updating dynamically, and you'll see the blend port valve also, updating the entire system in a transient fashion on the fly. So this, again, is a simple analysis of an electronic system, of a systems level model that can be integrated with ISPAC or with Fluent for electronics cooling. Okay, in summary then, we've got a systems level approach where we can use Flownex or Simplorer. It's good for the concept stage if you want to just see if your design is even feasible. It's good to get a top level idea of what's happening. We can obviously do a detail model where we have detailed 3D components, and that can be either using ISPAC, mechanical, AIM, which I haven't talked about, Maxwell, or a multi-physics type analysis. And then we have a coupled model. A coupled model can, include ISPAC talking to mechanical, Maxwell talking to ISPAC, or mechanical ISPAC and Maxwell talking to each other. But also, you can couple a systems model, as we've seen, a Simplorer model to an ISPAC model, or a Flownex model to a Fluent model, or an ISPAC model. With all these cases, we can have optimization, parameterization for operational and geometric conditions. With that now, I'll hand you over to Brian, who will summarize.
Okay, Joel. Well, thanks very much for that overview. We will start a Q&A session in a minute, so please post any questions you may have to the questions panel on your GoToMeeting window. Just before we do that, I'd just like to make you aware of some other upcoming webinars we're holding, which may be of interest to you if you're involved in the electronics and electromechanical industries. Firstly, in a couple of weeks' time, we will go into more detail about the link between ANSYS and Flownex. So ANSYS being obviously a 3D, FEA and CFD system, and how that can work very nicely with the 1D Flownex systems analysis capability. We'll also then be looking at a different topic, which is injection molding, and in particular some advice about how you can interpret the results of an injection molding simulation. This may be of interest to any of you who is involved with the use of plastics, and in particular injection molded plastics within packaging design for your electronic systems. We also have an overview on optimization techniques within ANSYS CFD, and in particular focusing on a couple of projects that we've been involved with over the last couple of years, which very nicely show the benefits and the applications of that capability. And finally, in June, we also have a separate session going into more detail about the use of ANSYS for drop test analysis. That is using the ANSYS Explicit STR program with a workbench interface, which allows the easy or relatively easy simulation of impact testing. In addition to that, we're obviously running a number of other events, so please visit our website at any time, look at our events page, the address is on the screen there, to see if there's any other webinars or indeed conferences that we're involved with which you'd like to attend. And finally, we're also always open to any more topics that may be of interest to you, so we would welcome you to suggest any future topics for webinar involving simulation, which we'll be delighted to present. Okay, so obviously we're pleased to take your questions now. If you have any other, I just say at this point, if you have any questions that you would like to ask offline, or indeed if there's anything you've seen today you'd like to discuss in more detail to see how it can perhaps fit into your own sort of design workflows in your company, then you'll see our contact details on the screen, and yeah, please call us at any time. So, just looking at questions, I have a first question here. Just a reminder, really, is to talk about can IcePack be run with Maxwell, with ANSYS Maxwell, in a transient simulation?
Yes, the answer to that is absolutely. You can. So you can either set it off where IcePack drives Maxwell or Maxwell drives IcePack. There's actually a tutorial on how to do this within IcePack. So the answer to that is yes, in a transient or steady state fashion.
Okay, that's great. Okay, yeah, we've got a second question just come in. You talk about, yeah, within Fluent, I know IcePack is based on, well, uses a Fluent solver. There is an option to customize a GUI. Can you also do that with IcePack?
I believe in version 16 you can do that. Obviously, customization can happen in terms of libraries, but also in terms of GUIs, so menus. You could do that if you wanted to. Yes, absolutely.
Okay. Well, I think that's all the questions we've been asked so far. I think we're coming up to our runtime now. So, as I mentioned before, feel free to talk to us offline if there's anything more that you'd like to understand about the use of ANSYS for thermal analysis, particularly in the electronics industry. Otherwise, we hope you enjoy the rest of your day, and hope to see you on a future webinar. Thank you.
Thanks a lot. Take care.